But I do want to talk about what it is and how it works because it'll apply to some things. So, when you have a solid material, it can be one of two forms. It can be crystalline, or it can be amorphous. So kind of going back to Chem 1 when you talked about things like sodium chloride. Now, sodium chloride is the poster child for ionic, and I'll show you, but it's a little oversimplified. In a sodium chloride crystal, which was the first one down this first thing, think if you have a sodium ion, and you have a chloride ion sitting next to it. But the chloride's actually a little bigger. They don't exist by themselves. This sodium, in this case, has chlorides on all those sides, plus one in front of the board and one behind the board. And there's another sodium here. There's another sodium here. And this goes out in 3 dimensions for billions of billions of billions of billions of billions of units at a minimum in a crystal. So by the time you can see a salt crystal, it has something like 10 to the 20th of these in a row in each direction. A lot. In a crystal. In an amorphous powder, sodium chloride rarely is amorphous, but you'll have this design over maybe 100,000 units. And then next to it, you'll have another 100,000 that is oriented differently. So you have domains, patches. Does that kind of make sense? If you've ever studied magnetic field, it's the same sort of idea. If you look at something like glass, normal glass is an amorphous solid. Glass is, ignoring the purity, is made out of silicon dioxide. Silicon dioxide, in its crystalline form, is a very nice mineral, okay? Highly structured. If it's partially crystalline, you know what we call that in glassware? Quartz. When you buy quartz glassware, or lead quartz, that's silicon dioxide that's basically on the crystalline scale, just not quite long term. But getting crystals is actually very difficult depending on the material. Table salt, calcium chloride, those sorts of things form crystals naturally. I will tell you in graduate school, we were trying to make crystals of new materials we're doing, and the reason you want nice single crystals is we can do this X-ray diffraction on them. X-ray diffraction tells us what's in there, how they're connected beautifully, great. If you don't have nice crystals, it doesn't work. You have to do something called powder X-ray, which is kind of. So the goal was to build nice, pretty single crystals. One of my office partners named Hailin Li from Nanjing, China. Great guy, hilarious, I have stories I'll tell you later. But Nanjing was a brilliant crystal chemist. I swear he'd run these reactions, he'd put them in the oven, come out like gemstones. It's like dice. Mine come out as mush. Problem was highly integral. I don't think new, throw it away. He sucked at the characterization, he was great at the making. So he made them, I characterized it, was a good team. But you need this for X-ray diffraction. So I'll do the scientific definition in a moment, but here's kind of a way to think of it, and it'll kind of give you an idea. If I picture a Tinker Toy model, a very complex Tinker Toy model. Everybody know what Tinker Toys are? Think of just the molecular models like you did the other day. A massive one of those with tens of thousands or billions of things in some complex shape. So I'm going to come in here, I'm going to turn on the lights. I'm going to take a very powerful flashlight, I'm going to shine it, and I'm going to take a picture of the shadow on that back wall. Okay? And I'm going to come over here, take a picture of the shadow. And I do this until I have a bunch of pictures of the shadows over in the room. And then mathematically, I take those pictures and figure out where all the atoms were. Because things move based on how far they were from the camera. Does that make sense? Incredibly high level math. Almost always done on supercomputers. Supercomputer in my my boss's lab, we had a liquid helium core underneath the desk. For reference, liquid helium is around 4 Kelvin. Also, we're running out of helium, by the way. That's a big problem. You know, all the helium balloons, terrible things from a scientific standpoint. Because we can't really capture helium in the air and use it. We get it out of rocks and minerals. Once they get it out of that, they put it in the tank and you use it in the balloons. It's gone. And a lot of our scientific equipment requires liquid helium to run. So, the answer is there are several other gases that make balloons float. Your kids probably just shouldn't inhale it for the talk. So, X-ray diffraction, I'm not going to go into detail, but I do want to mention this. And in Chem 1, you took chapter 7, which, depending on if you understood it, changed how you look at life because it told you everything you thought you knew is wrong, because it is. If I take two waves, and they don't have to be sinusoidal waves, but they do, and I run them together, if they're perfectly in phase with each other, what will happen when you add them?
Construction.
You get constructive interference. They double at the peaks, right? Cancel out. If they're perfectly in phase. This is the idea of a laser. A laser creates different variations. But a wave that goes down, it makes a point where when it bounces back on itself at the mirror, it overlays the exact same thing. So every pass, it's doubling its ability. And then when you're ready, you let it out. What's laser stand for? Light amplification through stimulated emission radiation. It's just a way to take a low energy wave and magnify it, amplify it by using the wave back on itself a bunch. Destructive interference, completely destructive, is when two waves hit in opposite phase. So if I let that wave run into this one, they'll add it to zero, right? Complete destructive interference. That's the fundamental idea behind noise canceling headphones. Noise canceling headphones do an okay job. Basically, they have a sensor that reads the ambient sound, mathematically multiplies it by -1, and adds it back to the wave. Which is why it basically makes it minimal. It's only good at certain frequencies, it doesn't work at others. It's reduced. That make sense? Anytime a wave interacts with the surface, you have interference of some sort. When the police officer radars you, what happens is he sends out a wave at a certain frequency, it hits your car, when it interacts with the car, the speed between the two causes the frequency to shift. And by the frequency shift, his onboard computer calculates your speed. And they can do all sorts of variations by rotating the angle, speed, computer handles all that. There are some problems with that. Not today. So X-ray diffraction lets us determine the atomic placement within a crystal structure. Okay. Very complex math, and we're not going to do it. The book gives a couple of minor equations. I'm not going to ask you those because they're really not useful right now. And those are just kind of the starting idea of the real math we can't do. And we don't want to do. But it lets us look at the placement of crystals. And crystals come in these repeating patterns, and they can become very complex. Did my computer sign off? It did. There it is. You do not need to memorize this part, but I do want to show you a couple of graphics just for visualization here. I'll do that at a time. So here's this idea where you take some source of X-rays, you run it through your single crystal, and as the frequencies interact with all the different layers, it spits out this elaborate pattern. That's that shadow on the back wall I use as an analogy. And then it changes the angle and calculates from the difference in the pattern. Objects that move further in each angle were further from the source, right? Or more that way. So what happens within a crystal, you have this elaborate pattern, but it does repeat. And you can go in and find the smallest repeating unit. What's that called? Smallest repeating unit in a crystal? That's the unit cell. They come in 7 basic varieties. You do not have to know these 7. There's an actual crystal liner here. Those are the 7. We're only going to worry about cubic, because cubic is the one that's simplest for us, and we're not trying to become crystalline. But they can come in fairly complex shapes. But we're going to look at a cubic cell. So in a cubic cell, you expect all the sides are the same length, and all the angles are 90 degrees. And a bunch of things can happen here as far as what's going on. But basically, if that was a repeating unit, I could take it and stack it, and I would create my crystal structure. And this can splice atoms in places, it doesn't matter. We're going to look at the 3, I'm trying to avoid a word, easiest simple cubic structures. The first of those is called simple cubic, sometimes called primitive simple cubic. And this is just where there's one atom at each vertex. I apologize for my drawing, I'll show you a better picture. There's an atom here, there, and that back corner that I'm not going to tell the drawing back. what fraction of each atom is inside the cube? 1/8. Because it's cut, right? There's 8 atoms, and each one is 1/8 inside the cube, so there's a total of 1 atom's worth of material inside. Make sense? That is a simple cubic. It has 1 complete atom. It really has 8 1/8. If you don't think of it that way. The next one we're going to look at is body-centered cubic, sometimes called BCC. It's exactly the same. It has an atom at all the vertexes, but it has 1 full atom sitting in the middle of the box. So now, how many total atoms are inside the cube? 2. The original 8 1/8 and then 1 whole one, right? And the third type we're going to look at, I'll show you better pictures, is a face-centered cubic. It still has the 8 on the outside, but now it has an atom embedded in each face of the cube. So there's an atom sticking out there, there, there. How much of each of those atoms is inside the cube?
4.
What fraction of each of these face atoms is inside the cube?
1/6.
Half.
I said half.
Here's the surface. Yes, there's a bunch of answers. You have the sphere there. And there's 6 of them. So 6 halves. So 3. So there's a total of 4 atoms inside the cube. I can't imagine anything be better than my drawing, but I'll try. So this one doesn't show the cube, but it might be somewhat the same. So here the simple cubic, you just have the 8 of them at the corner of the sphere they have drawn. These are the same ones. In the body center, there's also one stuck in the middle. And in the face center, there's one sticking out the front of each. Your book's going to talk about here coordination number. What is coordination number? It's the number of adjacent atoms physically in contact with the atom. So in a simple cubic, each atom has 6 immediate neighbors. Does that make sense? Yes.
Could you repeat the coordination number definition?
The number of atoms in immediate contact. Did I erase my definition? Remember that? I think I did. If you look at that sodium chloride picture I did earlier, look at sodium. It has a chloride to its right and its left, up and down, and front and back. It has coordination number 6. There's 6 atoms that it could touch. Does that make sense? In a face-centered cubic, each atom has access to 8 because there's another atom in it. And in a body-centered, face-centered, there's 12. Coordination number talks about how many atoms are directly in contact with the one you're interested in, or with each atom. And we'll look at that much more in 3 more chapters. I'm not going to ask you anything about edge lengths or about packing efficiency, but I will mention, you'll notice, simple cubic only fills a little over half the space. Half the space is not empty, because if you treat these as spheres, there's space where there's nothing there, right? And they go up and fill. The more filled the pattern is, the lower energy generally is. Nature abhors a vacuum. Empty space is an energy opposer. Better picture a little bit. There's a simple cubic idea. So what they've done is they've taken the spheres that were each vertex and just chopped them so you can only see what's inside. So see how there's 8 of them and there's 1/8 of each one in there? Simple cubic's not so bad. A little bit better picture of coordination number there, but it starts to get a little 3D. All this is in your book, of course. There's a body-centered cubic. It's maybe the simplest way to see it. You have the 8 on the edge like I did before, and you have 1 complete inside. So, for this gold atom, how many other atoms is it touching?
Well, 8.
8 is coordination numbers 8. And you can see that in all the diagrams, it's just easiest there, I think.
So with the coordination number, is it always based off of the central?
Each atom actually has the same. Yeah. Depending on the complexity, you can have different coordinations, but these are simple cubics. Remember, you can shift this over half a unit, it'll repeat with the atoms switch to their positions. And there's our face-centered cubic, a little bit better picture. You see the 8 edges, and these are half in, half of the outside. So there's 6 faces with half a sphere, so a total of 4. And there's that. Coordination number is a little bit harder to see, that maybe give you the idea. Clear back. You know, what you need to know on this is the number of atoms in each of the 3 types and the coordination number for each of the 3 types. That's the main thing. I will not ask you to draw this. Because I can't. This next part, in my opinion, is really obvious, but it's not. So let me ask you one of those Chem 1 questions, week 2-ish, this tournament. So try this one. What is the mass of a single aluminum atom? Try not to spell this word. In grams. What's the mass of a single aluminum atom in grams?
Do you want an interdimensional analysis or just automatic?
Your choice. And I don't care about the number, I want you to go tell me how. I'll get the number in a minute. You can do it dimensionally or you can do it logically, they just leave the same place. What's the mass of a single aluminum atom in 1 gram? We're using the because then it would be asked. They'll all be similar though.
What's up?
When you have an answer, I'll come take a look and we'll talk about it. That looks slightly different than mine, I'm wondering why. I probably wrong. But yes. Let me ask you one of the stupid questions. Let's assume everybody in here weighs the same thing, all right? If I tell you all together, we weigh 14,000 pounds, I should have done the math first, I didn't. How would I find out the weight of each person? Just divide by the number of people, I think that's right. And I'd get the weight of each person, does that make sense? Yeah. Same thing here. On the periodic table, aluminum has a number underneath it, depending on which table you use. We should use the one I gave you. But aluminum was 26.98154, right? Pseudo trick question. What are the units on that?
Grams or moles?
It has 2 different meanings. 26.98 what? 154? Was it? Thank you. It could mean grams per mole, and that is the molar mass. And again, it's silly to think that molar mass is the mass of a mole. Or it means 26.98154 AMUs, and that is the atomic mass of an atom. They're not the same thing, they're the same number. This is how much one atom weighs in AMUs, that's how much one mole of atom weighs in grams. So the simplest way is I know Avogadro's number with 26.98. Divide by Avogadro's number. And you get the weight of each one. Should be around 4.4 times 10 to the negative 23rd, depending on which. That makes sense? If you use my periodic table, you should have gotten 4.48 times 10 to the negative 23rd grams. By the way, in Chem 1, they might have told you or showed you a way to convert between AMUs to grams. You don't need it. They're literally, it's written in the definition. To convert from AMUs to grams, all you do is to 1 over Avogadro's number. The reciprocal of Avogadro's number is the conversion, which is kind of neat. Second question before I jump into this. What's our definition of density?
Mass over
Mass over volume. So, You can think of this next thing as a formula if you want. It's not on your formula sheet because it's logic, but density equals mass over volume. So if I want to get the density of a unit cell, I need to weigh out how much mass is inside the cell divided by the volume of the cell. Does that make sense? The mass in the cell will be the number of atoms times the weight of each atom. And the weight of each atom will be its molar mass divided by Avogadro's number.
That's a D?
That's an N times M sub n molar mass.
Density.
That's rho. D is not, density is not D, density is rho.
Alright, so.
Yeah, at least at the freshman level. D is reserved for something else. Greek letter rho, there's like the curly D. That's the mass inside. Does that make sense? This is the weight of one atom multiplied by how many atoms there are. Good or bad on that part? What's that? N is the number of atoms inside the cell, which for simple is 1, for face centered is 2, sorry, for body centered is 2, for face centered is 4.
Because I always get N with moles, so like, because of the BB.
In this case, it's just number of atoms.
N is,
We'll run that letter
wait, so
long.
N is moles.
Divided by the volume, which is side cubed, because it's the cube. Does that make sense?
What?
The side, the length of the side, the
Oh,
unit cell.
okay.
You can use L or S for the volume, your choice. And that really just says mass per unit volume. So given those sorts of things, you can find the other.
What's S in this case?
S is the length of the side of the unit cell.
Oh.
If you use L, go for it. So I'm going to tell you that iron forms as a body-centered cube. Now you wouldn't know what type of cube a particular thing does without being told. I have to tell you that. And I'm going to tell you that iron has a density of, I'm going to tell you iron's density in a minute because I'm changing the problem. But I'll give you the number. I want you to tell me what is the length of the unit cell? How long is the side? The length of the unit cell in iron. I want to say 7.4. 7.86 grams per milliliter. What's the length of the side of the unit cell? It might shock you how much information you can get from this suddenly.
Was that grams over milliliters?
Yes.
So in the original equation, you have density equals the amount of moles times the molar mass over.
That's not moles, that's number of atoms inside. N is the number of atoms inside the unit cell.
Okay, then what was N sub n?
Avogadro's number. Units. If you're losing significant digits, you put your calculator below where it does on. Type in something rotation. Alright, your calculator moves, yes. So
You have to cube it.
I think so, yeah.
Oh, no, I'm right.
You keep everything in there.
I waited for you to go because I didn't know what to think. I look at you and I still don't know what to think.
That's not supposed to happen.
Okay, so this is what.
To the wall. What are you doing? One more?
All of that divided by.
Okay, so then we'll assume that we're doing one more.
Unless I typed it in wrong.
There's two different things. There's three for one.
What did you get?
The bottom
I don't know if
is the number of atoms.
Okay, so you found like the M
I don't know.
Yeah, but I did my work for, we start off with this and then I moved some stuff out and then I pushed
Bro.
Just doing the algebra symbolically?
Wait, I'm still going. I'm still going. Wait, what?
How are you multiplying it by 2?
Yeah, well, I'm playing about two, that's how many atoms.
What's giving you trouble?
Per body center.
I got the, okay, so I got the cube root thing.
Okay, that
I
makes
have,
sense.
wait, hold up. I'm not.
Divided.
Okay, before I even start putting number in, I have S equals the cube root of N over the M sub M, and then
And over M sub M.
M.